Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So good afternoon, folks. It's my pleasure to welcome Mikola Paczynski, who's at the University of Eindhoven, where he's been for, what, 5 or 6 years? 7, okay. And he's done a lot of work in the area of social media analysis, the area of information dynamics, how information changes over time, and in fact, he's going to talk about that today. But a lot of his work strikes me as a leading indicator of what we see now in data science, where you have interesting real-world problems, largely scaled data sets, and thinking about new ways of capturing some of that in the large-scale logs. So it's my pleasure to introduce him. And today he's going to talk about how to handle concept drift in predictive modeling, because the world is not a stationary in IID. And so it's an absolutely important question that a lot of the models overlook. So it's fun to hear about it. Thanks.
Good afternoon, everyone. It's my pleasure to be here and an honor to be here. And thanks, Susan, for a kind introduction and giving an opportunity to give this talk. So today I will talk how to get ready for change. And I provided a subtitle for the talk for disambiguation, just to make sure that this talk is not about climate change, not about global warming, or not about regional cooling. So these are a couple of pictures from Dallas a few days back, but probably you saw more on TV. So I'm going to talk about predictive modeling, and many of you know that making predictions is a hard job. Quite a few wise and very experienced people during their career made quite a few predictions. Not all of them were correct. So you might recognize some of the famous quotes about how, well, like what is the potential of new technology, if it's going to take off, and so forth. But these are different kinds of predictions. So these are based primarily on the expertise and intuition of experts or gurus. So I'm going to talk about data-driven analytics and the problem of concept drift. So the outline for the talk is very straightforward, very simple. So I'm going to explain what I mean by predictive analytics and why is it important to consider concept drift, what are the typical approaches to handle concept drift. And after that, I will try to emphasize that actually from applications perspective, it's interesting to see how many challenges have not been addressed yet from research perspective, and what kind of interesting opportunities for further research it provides. And at the end, I will make my own forecast or prediction how the field is likely to develop further. So by predictive analytics, I just take a reductionist approach to say, well, essentially it's about data mining, about knowledge discovery. We have a possibility to collect large volumes of data, process this data to get some useful predictive patterns, models, summaries, which can give us an insight into a phenomenon, and get us some actionable patterns and things alike. So the most basic supervised learning settings may be presented in the following way. We have some historical data that tell us how our target population behaves. We can induce a model from this historical data such that given previously unseen instances, we can generate a label. Like, for instance, we want to build a classifier to determine which of the emails are important and which are not. So based on the previously collected emails and knowing which of those were wrong and which of those were relevant and which were not, we built a model. So next time when you receive a message about a talk like this one, you can be sure you will not miss it. And then you can think about various types of predictive modeling tasks. So would it be classification, like determining relevance of an email, or finding out who the user is, performing user profiling, understanding whether this is a novice user or an expert, or what kind of information need a user has, and so forth. So we can think about various types of regression tasks, like for instance, making the predictions how you would score a talk like this one, or performing ranking in case of search engines, in case of recommender systems, or perform time series prediction. For instance, when we want to estimate the popularity of our website, when we want to predict the amount of traffic we can attract or click-through rate on a particular banner or news item, and so forth. So there are lots of approaches for predictive modeling for each of these tasks. In this talk, I will focus primarily on classification examples. However, most of the discussion we will have can be related to other predictive modeling tasks as well, including ranking, prediction, and so forth. So if you think about geometrical representation, you can consider like number of instances which are represented in some multidimensional case. They have labels which represent the which tell us to which class they belong, and we have a true decision boundary which allow us to discriminate instances of one class and the other class. So if you ever tried to build a predictive model in practice, you're familiar with lots of major pitfalls. Like we need to have clean input, or at least somehow reasonable input to build a good model. We need to come up with representative features. We need to come up with the right problem formulation such that we optimize for the right things, avoid overfitting, avoid false predictors, think carefully about operational settings, what is known to us when, what kind of attributes are descriptive, predictive, which attributes we can manipulate, and so on. However, I would like to focus on just one single aspect related to the problem of concept drift, which in my opinion is less studied in different research communities and even more so in practice. So think about the following problem. We want to find out whether a particular antibiotic is going to be effective or not against certain type of pathogen. So we have historical data about patients, about their demographics, hospitalization data, and we know for which patients some antibiotic were effective or not effective with respect to certain pathogen. So we can use our favorite classifier to determine whether certain type of antibiotic will be effective or not given a new patient. However, the problem is that the problem is that different pathogens can develop resistance to antibiotics over time. So a classifier which was effective in the past, over time may become ineffective. And this may happen due to various reasons. So the following cartoon gives the main intuition. So one of the pathogens can develop resistance, and once this is performed, actually there are different ways how this information can be communicated to other pathogens. So just piece of information can be given to the other pathogen, or there could be a case of so-called microbial sex, or other type of relationships that can spread the information about resistance and make pool of antibiotics currently used at the hospital to be ineffective. So the goal is to find out when such things happen and find out a way how the model should be adapted, adjusted to keep them up to date and useful. So when we think about streaming data, we can think about different types of situations or different reasons why things may change over time. So think about 4 different characteristics examples. So we can think about changes in personal interests, like think about recommender systems or search engines. When we try to figure out what people are interested in, we build a user model, build a user profile of short-term, long-term interests, recurrent interests. And because many of those are not stable, we need to monitor for those changes. Think about email classification example when we want to identify which emails are relevant, which emails are spam. We can build a classifier which is accurate at current moment in time. However, some of the spammers, unfortunately, are quite smart. So they try to bypass the spam filters and they develop new strategies how to generate emails. So we need to deal with these adversary activities, again, recognize them explicitly through the analysis of input stream or monitoring the performance of our classifiers to identify these changes and adjust to them. So you can also think about changes in population as such. So think about economic crisis that changes the profiles of people who apply for credit. So in credit scoring application, again, we would need to account for such global changes and relearn the models. So finally, you can think about complex environments where we can explicitly monitor lots and lots of pieces of information. However, it is very, well, it's intractable to model all possible combinations of factors, and we just need to reduce the modeling only to those few elements which are critical for our application. So like many of you might be familiar with DARPA challenge of driverless cars, and Stanley Winning team was describing how they use adaptive learning strategies to analyze whether it's a drivable surface or non-drivable surface, if it is paved road or unpaved road, and different lighting conditions and things alike. So simple adaptive learning strategies can do the job. So many of you are also familiar with a Netflix competition where, again, lots of different ideas were proposed, different factors affecting the performance of predictive models were studied, and then part of it was related to temporal dynamics related to ratings, how items become more popular over time, how for instance, item side effects can be observed, user side effects can be observed with respect to rating scale, with respect to user interests, with respect to popularity of the items, seasonal effects, and so forth. So from machine learning and data mining communities, people tried, or sometimes they emphasize the difference between real concept drift and virtual concept drift. So think about our original example when we have instances belonging to two different classes and we have a decision boundary. So we talk about real concept drift when with true decision boundary changes. And then we need to update our classifiers to relearn this new boundary. However, there could be also different reasons for virtual drift, when the true decision boundary remains to be the same, but the distribution of data changes and it affects the performance of classifiers still. So, as discussed, these different cases can be decomposed even further. However, from predictive modeling point of view, as soon as changes in the data or in the labels or in decision boundary affect our prediction decisions, we need to detect this and decide what to do next. So if we go back to the basic supervised learning idea under concept drift, so now we need to question whether the population about which we had some historical data learned our model is still the same or it's different. And if it's different, what shall we do with our model? How we are going to update it? So we can think about two major approaches, like how to manipulate the training data, how to select the most representative, for instance, the most recent instances, and how to perform model update or relearning of the models, whether it's a single model or an ensemble of multiple approaches. So we've been looking into different strategies and some general high-level framework which would allow to describe major types of approaches for handling concept drift, and then it can be represented with the following simplified view. So we have input data. From this data, we learn a model and we cast predictions. So besides that, we accumulate some relevance feedback about the performance of our models. We monitor our input data. We monitor how well our classifiers perform, and if we detect changes, we can manifest them to our data management system or learning subsystem such that it becomes more up-to-date and then can generate more accurate predictions. So besides that, we can also alarm the identified changes either to the main expert or to other submodules of a system. So consequently, taking this perspective, you can think about various types of ways how to characterize major approaches for handling concept drift. With respect to memory management, different types of change detection techniques, how to characterize the properties of learning techniques, and how we perform the monitoring and evaluation of these learning approaches. So when we talk about memory management, you can think again about short-term memory when we have a small portion of data that we keep in main memory and we can use for building a model. Or you can also think about long-term memory, which is captured in the models themselves. And effectively, you can think about various strategies, how to maintain this training window of fixed size, variable size, how to introduce some forgetting mechanism such that we, for instance, downweight the importance of instances which were observed far in the past and then boost the importance of most recent stuff.
So you're talking about it as if you get the same treatment for every, we'll say, query or every instance. Do you look at all at models that may have different, say, forgetting functions for different queries or different subsets of data?
So this is a very good question. I'll try to come back to it a bit later during this talk. So the mainstream of concept drift research assumes that we deal with a single object. So for instance, we have a time series data that tell us something about an industrial process. Or we talk about an individual user and we monitor interests of this user. So think about like a single classifier or single learning mechanism. But you're absolutely right. So in many cases, we have a multitude of objects that we trace over time, and it makes perfect sense, on the one hand, to build different models, and on the other hand, try to learn from multiple objects such that they contribute to each other. However, in the most basic settings, it's considered to be all uniform. So we have similar kind of data about similar instances. So with respect to change detection, again, you can think about various types of approaches, like what can be monitored and what kind of analysis we can perform, like for instance, sequential analysis, like cumulative sum test, control charts, monitoring of two distributions, using some contextual monitoring and things alike. So from the point of view of properties of the learning models, again, we can think about various types of categories. For instance, whether we perform retraining of the models from scratch or we try to apply some online or incremental learning, whether our models are informed about accurate change or we perform evolving or blind adaptation. So we don't know whether change happened or not, but we do anticipate it and therefore we update the models. So finally, whether we build individual models or try to maintain an ensemble of individual predictors. So this can be discussed in a much more fine-grained way. However, instead I would try to focus on four major categories and give an idea how simple these approaches could be. So we can think about four major types of approaches. So in the first case, think about use or not use of detection mechanisms which would trigger information about the change and trigger an update in the model, versus evolving approaches which just adapt models every step. So we don't know whether change happened or not, but because we know it may happen, we perform the adaptation. And on the other side, we can think about individual models or ensembles. In the first case, typically we think about some reactive modeling with some forgetting mechanism, or an ensemble approach which tries to maintain some memory over time. So, for instance, we can think about simple forgetting mechanism when we have a fixed sliding window. It goes over time, so our model is retrained or incrementally updated with analyzing new instances and forgetting the most outdated ones. So very simple approach, but can lead to some reasonable results. So the next one is based on explicit detection of a change. So again, we have training data, we have a change detection mechanism. Once we detected that there was a change, we disregard the data which is no longer relevant and build a model on the new stuff. So again, you can think how we can hunt for useful information about the change, whether it's in the input, in the model itself, in the output, or analysis of performance of the models. So all of this can be useful for manifest change. So most frequently, we analyze two windows of some statistic, which can be again computed either on input or model parameters or outputs. We have a reference set on which we assume this is the current stable behavior of the model. Then we have the most recent set. We compare the two, and if there is an observed difference between these two sets, we manifest a change. And then different statistical tests can be used for that. So we can build an ensemble of classifiers to track how well different models perform. So again, think about timeline. We have multiple windows. On these windows, we build classifiers. Every time we need to cast a new prediction, we ask every classifier to cast a vote and apply some voting mechanism. So think about the initial situation. We have multiple models and initial weights. They all cast the prediction. We know what is the true prediction. So those guys which were correct get a higher weight. Those who were wrong get a lower weight. And we keep doing this. And this way, we always maintain a pool of classifiers and knowing which of those are the most adequate or the most accurate to the most recent data. So finally, we can think about some contextual approaches where we try to identify regions in the data. For each of the regions, we find out the most suitable classifier, which has the highest accuracy or the highest generalization performance on that piece of data. And whenever we have a new instance to classify, we check in the instance space what are the other similar guys to this and apply the corresponding classifiers which are expected to perform best in that neighborhood. So given these different types of techniques, we also can think, okay, well, which of those are most effective or which of those would be useful in which of the settings. We can also think about different kinds of change, like whether it's a gradual change or sudden change or recurrent change. Is it expected somehow? Is it predictable or is it completely unexpected? And consequently, in which cases we can be reactive or where there is room for being proactive, like anticipating change, making predictions about it, and making models ready to use. So if we look into these four major groups of strategies for handling concept drift, whenever we deal with sudden drift, so usually this reactive models based on explicit change detection and some forgetting mechanism would be doing just fine. For sudden drift detection, ensemble approaches can deal with gradual drift, and for recurrent, we need to have some form of meta-learning, some form of context awareness to capture recurrency or recurrence of particular concepts. So given this overview, of course, there is also a question how well these different approaches work in practice. Why do we need so many? And if there is no one best approach for all the situations, how we are going to choose the most appropriate one for a particular application in mind. So many of you might be familiar with cross-industry standard for data mining. which was proposed some years ago, and then it was appreciated by the industry because it specified different steps in the process, like starting from business understanding data preparation, to data mining, evaluation, and deployment. And then each of the steps was described with respect to operational settings, what are the useful things to take into consideration, what are the available techniques to be used, and so forth. So now, if you look into streaming settings, effectively all of these feedback loops, which in the past we assumed to be performed by domain experts. So the domain expert would see how well a particular model performs and then try to fine-tune the parameters, or to reconsider what kind of technique to be used, or reconsider what would be a good representation, and so forth. So now, in streaming settings, we try to automate all of these feedback loops as much as possible. So we monitor the performance of classification models or predictive models, and whenever something goes wrong, we need to take a decision how to update the model, how to change the representation of the data, and so on. So we were curious to see what many people think about applying concept drift in practice, and we did an extensive literature analysis to see how well different techniques work in practice, or at least how different researchers believe they work in practice. And we did also quite a few case studies ourselves, and we were surprised to see that some of the popular approaches might work or might not work. And we were trying to figure out what was the reason, and which of those techniques are in general applicable or not applicable for particular operational settings. And we realized that in the area of concept drift research, the situation was quite similar to early days of machine learning and data mining. So many researchers say temporal dynamics is important, concept drift is important. But then real data is hard to get because of privacy concerns, or some proprietary reasons, or because there is too much overhead to work with real data. Or sometimes people come up with a too generic or too abstract solution, so it's not ready to be used in real applications. So what we often can see, people play with benchmarks or artificial data sets, and then try to generalize from those experiments. However, because in data mining, many journals, conferences, reviewers argue that, well, this is an application field, so you need to show the relevance to practice, you need to show that your methods do work in practice. So many people try to invent applications and show that the ideas do work in practice. And this is something I relate to the problem of green aliens, and I will say about this in a minute. So in case of concept drift research, at some point it was really close to some extreme. So people were playing with artificial data. There were a couple of benchmarks extremely popular. This particular type of concept drift simulated, and then in many cases people were also trying to use standard UCI benchmark data sets, manipulate them in a certain way such that concept drift would be introduced, and then it would be captured by certain techniques. And in my opinion, this is really close to the situation described in this paper that I really like. So it's called Novel Efficient Automated Robust Eye Detection System for Green Aliens. And it describes the situation in the field quite well. So this is a sarcastic short paper, and it's a very quick read, and I strongly recommend to look at it. So this triggered us to rethink once again what kind of methods we have, and in what kind of application settings they can be used, and what is the variety of application settings where concept drift matters, and we actually need different types of strategies to handle it. So we did very simple thing. We tried to identify different dimensions along which we can categorize or characterize various types of applications. For instance, with respect to what types of data is being used, what kind of problem formulation we have, what kind of changes we anticipate, and various types of operational settings we need to consider. So with respect to data, again, like, is it time series data, relational data, or mix of those? How data is organized? Is it a high-speed stream, or is data coming in batches? Can we reaccess the data? How to deal with missing data and things like. So with respect to change, well, like what kind of types of change we can anticipate? Is it just single type, like only sudden or only gradual, or simultaneously in the same application, different types of changes may occur? What is the source of change? Is it about adversary actions or changes in population? Or again, it could be multiple reasons present at the same time. What are our expectations about change? And what are our expectations about desired actions if we know that the change appeared? Because actually, again, it really matters what we are optimizing for if we know what the goals are. And with respect to operational settings, again, we need to be very careful in understanding whether labels are available to us immediately or with some delay, or they are never available. Are they available as a ground truth or some proxies as for ground truth, or we can just pre-compute from historical data, from offline data, how likely it was that we were correct or not correct, and other things. So we also analyzed various types of applications per industry, like in finance, in banking, in security, in e-learning, entertainment, search, recommender systems, things alike. And we tried also to categorize them by different types of applications, like whether it's about monitoring and control, or whether it's more about personalization tasks in search and recommendations, whether it's more about management and planning when we need to perform demand prediction tasks, or some ubiquitous applications when we have, for instance, location-based services or other things which are integrated in other larger systems. And then actually we analyzed with different types of applications and saw what kind of drifts typically occur, how frequently we have or do not have labels available, how hard they are, how objective or subjective they are, and so on. And we also started to look into different methods and what we have and what we don't. And it's interesting to see that if you look into mainstream research on handling concept drift, this would be the most assumed settings. So change is typically considered to be unpredictable, typically it is sudden. So if we observe multiple changes over time, they are considered to be independent of each other. So there is no opportunity to learn from multiple recurrence of changes. So typically we analyze only a single object, so we don't analyze multiple objects. We assume no closed loop control, so there is no effect or there is no reinforcement on the behavior of a particular system. So if it's even adaptive application, like a recommender system or information retrieval system, again, there is no assumption about the biases in the data. And typically it is assumed that given historical data, we can replay it multiple times and fine-tune the parameters and get reasonable estimates how well a particular technique would perform. And then besides this, most of the approaches for handling concept drift assume that the true labels are available right after casting the prediction, which you can imagine in practice is rarely true. So in reality, if you think about wide spectrum of applications, changes often reoccur multiple times for a given object of interest, but they also reoccur across multiple objects with related behavior. So typically we need to monitor for different kinds of changes. So beyond this, we can think about a multisensory environment or multisensory data when the same object is being described by different feature subsets. If they are analyzed independently, they give somewhat unreliable signal. However, if we analyze them together, they can help us to detect concept drift much better. So in many cases, we have no idea what the ground truth is, so we can also get some guess about it. In many cases, we know quite a few bits about the process we model, and this background knowledge can be utilized to build better predictive models, but also have better ideas about what kind of changes we anticipate and how it can be detected.
Do you see many examples where the ground truth changes over time? Or at least the labels change? I'd say the ground truth changes over time.
Right, so there are a few aspects. So you can think about change of label like a simple change in interest. So assume you have a classifier which determines whether a user is interested or not interested in particular topic, like soccer. And over some period of time, you observe that a person was interested, and then you keep recommending items about soccer, and then the user doesn't click. So this is change in ground truth, in a sense that, well, you know that user had this interest, now the user changed the interest. But what I also mean here is that in many cases, we cannot make an association between the labels and the ground truth. So we collect information, like for instance, we collect implicit feedback, but we are not sure if this corresponds to actual interest of a user. Or in many cases, when we deal with sensory data, so the goal is to reconstruct the signal. So we don't know what the ground truth is. So we try to predict it. And then based on analysis of historical data over a long window, we can reconstruct this ground truth with certain degree of certainty. But we're still not sure if it is ground truth or not. And this is also quite important when we try to optimize the performance of techniques on historical data. So we can fine-tune the parameters for optimizing for labels, but effectively those labels can be quite noisy, and we're optimizing for one thing. So consequently, like if you look into these peculiarities of various types of applications, we can think about more advanced approaches both for reactive and proactive handling of concept drift. So whenever we think about recurrent changes, there is a room for meta-learning approaches, how to recognize similar situations from the past, and use more accurate detection and prediction. So whenever we know that there are different related sources of data, so we can learn from that external data, which can be considered in centralized settings, but also in distributed settings. And then we can think about context awareness approaches. So I will try to give a few ideas of each of those. So regarding the context, so think about the problem of outlier detection. So if you have some seasonality in the data, it's not sufficient to perform simple thresholding. So we need to have some approach which would capture the seasonality. So similarly, when we want to perform change detection, we may want to figure out like what is the normal behavior of a particular system. So here is a particular example of sensory data. The goal is to reconstruct the true signal. This is just a mass measurement of fuel in an industrial process. And it's very clean task, like it's very easy to formulate. So every moment in time we need to say what is the actual value of this time series data. So we need to get rid of noise, we need to detect change points, like determined as with red circles. And we need to do this as quickly as possible such that we start relearning the models again and again and again. So there are quite a few challenges to address here, like asymmetric outliers, also some distortions in different phases of the process. But there are more things to that. So first of all, because we see that there is a clear pattern, like we have one phase when there is fuel feeding process and fuel consumption process, and then they follow each other. So we can try to see how we can get information about this periodicity and make use of it. So another interesting aspect here is that there are different factors which affect the behavior of this time series. So for instance, different fuel type would affect how many outliers we have, and then some other properties of the signal. So if we know some of those factors and we can model them explicitly, again, there is room for meta-learning approaches where we can learn models for different types of fuel. So in online settings, we can recognize what is the current quality of fuel or type of fuel and apply the corresponding model, which would make a better use of the data. So another type of problem is demand prediction, like predicting how much traffic we can attract on a certain time of the day or for a certain type of query, and so on. So we studied this problem in case of food wholesales prediction, which was important for a company for stock replenishment. So if you underestimate the demand, there would be empty shelves. If you overestimate the demand, there will be lots of perishable goods wasted. There are also interesting moments how badly you can do if you predict the demand too late or too early, what kind of costs associated to it. So this problem is difficult as such, because it's hard to predict behavior of people when they want one or another type of product and in what quantities. So we formulated this time series prediction task, which was augmented with lots of information about weather, about calendar, about holidays, about promotions. So we were trying to make the predictions. And actually this project started very interestingly. So the company said that they were using simple moving average to cast the predictions. And you think like we will use any state-of-the-art predictor and we'll do much better. And then we picked like few dozens of nicely behaving time series data. We applied some simple ensembles of regression models, and then we got somewhat better results. Like at least it would beat 10 to 20% the moving average that was used. So we were quite encouraged. We talked to the company, showed the results. They gave us much larger pool of products. It was like several hundreds of products. So we applied the same model. We compared it across multiple products. Our models were worse than moving averages. In fact, there is a good explanation for that. So many of these products are simply unpredictable. So if it's just noise, doesn't matter how hard you try to predict them. If there is no signal, you cannot do much more than just smooth out the signal. And we reformulated the problem into like how to determine which of the products behave somewhat in a predictable way, and for those which can be predicted, for those we can use intelligent predictors. Otherwise, we just need to apply smoothing, and we cannot.
Can you give an example of an unpredictable food? Milk, presumably, is reasonably predictable.
Actually, many of the products are hard to predict because you don't know when the season starts and season ends. So, for instance, even for
so
exactly. So there is seasonality, and even for those like simple cases, when you know, for instance, that ice cream are better sold in summer, or meat is better sold during like nice weather. But sometimes it's very hard to know when in mind of people it's already summer, or if this weather is indeed good weather. I can tell you more, just a bit. So So the way how we continued, we started to think, okay, well, if we cannot make good predictions by analyzing individual products, maybe we can collect information from multiple related products, and then we can do better predictions. And obviously this can be done in different ways, like for instance analyzing the taxonomy of products, hierarchies, like doing sort of content-based analysis and performing clustering and then building models for each cluster. And I thought this would be the most intuitive and the easiest thing to try out. And I must say that I lived in Finland for a while, and then there are a few types of beer, and typically in Finland people go to sauna and they take beer with them. And most of the beer tastes alike, and you would expect that they behave similarly. Of course, I didn't realize that once you move to Holland, and when you have hundreds of different types of beer, of Belgian beer and Dutch beer, the situation is a bit different. So there is beer that you have on Christmas, beer which is more popular on hot summer days, in the fall, etc., etc. So it's not just about different glasses which you need to use for different kinds of beers, but it's also about different habits, what types of beer you need to drink when. And therefore, we quickly realized that, okay, well, analyzing just descriptors of the items is of no help, and then we need to analyze the behavior of different products and then see how similar they are, and then based on this analysis try to build group models and then see how better we can do. And indeed it gave some improvement, but still it was amazingly difficult task, difficult predictive task. So what we did end up with, we tried to figure out when we can determine some seasonalities, when we can determine external events, discontinuation of products, new contracts, appearance of a product which is complementary to some other products, and so on. So it was interesting study with quite a few lessons. So you can also think about distributed settings. So for instance, distributed classification, when you have multiple hospitals, they perform diagnostics of certain disease, they accumulate data. Quite often they cannot share data with each other, but they can share models, or they can share some patterns. And then, for instance, in case of antibiotic resistance, this would be an example when you know that something is going on, something is happening, change is occurring, so you need to update the model. So perhaps similar changes may occur at other hospitals, and you want to alert them upfront. The same way, like when you are on highway and you see a traffic jam, so if you suffer, you want to notify people behind you, be prepared. So, say similar mechanism can be analyzed for handling concept drift, and this is something that we've been also doing in the recent past. So think about, oh well, actually this is also a real example of how the weather pattern looked one day before I had to go to Dallas. So most of the flights were cancelled, but luckily the weather changed, and then the day after it became much better. Anyway, so the idea is that, again, we have distributed settings, we have multiple weather stations, and then whenever you have a cyclone with some warm weather or cold weather, you can anticipate that when you know direction of the wind and when you know about the connections, you can proactively anticipate changes of the weather in the related regions. So this idea can be considered in multiple settings. So think about social networks, or think about other ways when one object can affect other object. There could be different kinds of relationships that can be learned from historical data. So we studied the settings of handling concept drift and peer-to-peer settings. So again, assume that there are multiple peers. Each tries to build a classification model for instance, casting classifications for positive, negative class, and different concepts are being observed for each of the peers. And if you see how those change over time, you can see that actually there are some relationships between the peers. So for instance, in this case, something that we observed for peer A would be later on followed by, will be followed in peer 1. And this is quite a strong pattern over a long period of time. So the problem is how to analyze these dependencies, how to mine rules or episodes which would tell us how likely it is that change in one peer would manifest a change in the other peer with certain delay and with a certain level of confidence. So once you can solve this task, you can think about building different adaptive learning strategies. So in our case, we come up with an interesting ensemble learning approach where we would maintain two pools of classifiers, like reactive classifiers, which monitor for the peer itself what things change, and a pool of proactive classifiers which are based on the information that is acquired from other peers. And we came up with an efficient way how to learn the dependencies between the peers. Another interesting aspect is how we can develop trust of the users into what we do. So this is generally a very important problem in recommendation tasks, in retrieval tasks, in predictive modeling tasks. So now we have yet additional layer of complexity. So we want to explain not only predictive models, but we also want to explain the change, like why this is a change, what might be possible cause of a change, what we can or should do to the model according to this change, and so on. So here I would like to give you an example of stress analytics to tell what interesting aspects. 10 minutes. Okay. Yeah. So I'll give this case very briefly and then try to conclude. So think about basic notion of stress. So there are different stress factors, like for instance, given the stock. So we have our sympathetic system, which is sensitive to these stress factors, and our body can react in different ways. Like the heart rate may increase the sweat production, other things. And then we can build devices, well, similar to this watch-like devices to monitor these physiological signals. And then once you detect a change, you beep and alert a person that he or she is stressed. Well, maybe it's not just about online alerting, but about accumulating this data and making people aware of how much they are stressed, during what times of day, during what kinds of activities, and so on. And then this was an idea we explored from different perspectives. So we've been trying to build a framework which would allow to accumulate information about different stressors, about typical activities that people perform during the day, so all kind of agenda or calendar data, and then link this data to actual stress patterns that were detected. So most of the work was related to analysis of galvanic skin response data. So like we monitor increased levels of sweat production, but we also played with analysis of voice signals and trying to mix these few things. We also tried to link information from personal correspondence of people, like linking their Twitter account, Facebook account, email account, to see how much positive and negative stuff is being said, or how much positive and negative stuff you get from colleagues or from family, and so on. And then once a sufficient amount of data is collected, so we can also do some interesting pattern mining, like to analyze what kind of activities bring more stress or less stress. But I must say, this is not the part where we are. We don't have that much data to do this part. But what we've been doing, we were trying to analyze with different patterns of stress and how those can be detected. So typically what you can see or expect to see is the following pattern. Like first you're in a normal state, then there is quick arousal, then there is this aroused state, and then there is relaxation period, and people are back to normal. Well, in practice...
normal, do you mean normative or normal?
Oh, this is a good question. It might take me more than 10 minutes.
Okay.
But to give a very short answer, I thought that a lot of information is known about stress, and we will contribute from computer science point of view, like how to analyze the patterns. But the more I read about stress studies, the more I understood that actually not that much known about stress. And in my opinion, what is normal is a very good question. I must have a slide on this too. So in practice, the detection of change is somewhat different. So you can have all kinds of noise in the data, which needs to be processed. There could be all kinds of external factors, like people doing exercises. There could be loose contact with the device and all other things, which bring, again, interesting additional things to consider. So here, interpretation of the signal is extremely difficult. So here again, like we don't know the ground truth, and it's very hard to obtain it even in control settings. So well, you need to find out whether the person is stressed or not, how much stressed, what would be evidence for that, and so on.
Do you at least have metadata in this?
Hmm?
Do you have metadata in this? Like
For some,
eating, sleeping.
For some, we do. So we conducted some pilot studies. What I personally did, I ran some experiments with students during exams. And I was asking them to report, well, of course, in anonymous way, like for which questions they thought they would knew answers, for which they wouldn't know, and this kind of stuff. So then in a couple of courses, I have poster presentations of project results. And what I was doing, I was wearing the device, and I asked people presenting the projects to wear the device, and then to see how much people are in the arousal state when they present the project to me, or when they present it to their peers, to other students, or when they listen to the other presentations and things like that. So now in Eindhoven, there are also studies with school teachers. So there is some interesting data. We also conducted really controlled experiments with a small group of people. Like there were 12 people, and we were actually running different tests to stress them out, and then see the reaction, and see how this would be reflected in GSR and in voice, and then so on. So we also formulated this as a classification task, and we were trying to find out what kind of other data we can collect, such that we can disambiguate different cases, like whether it's about physical exercises or real stress, what would be possible reason for the stress, and so on. So again, in many cases, you think about how to study the phenomenon versus how to come closer to actual application, such that you can still use a small device and then use, for instance, accelerometer data to recognize activities. And then once you know activities, you can disambiguate better. So as also mentioned, we analyzed GSR and speech, also some interesting results. So apparently speech is much more discriminative. I mean, it's much more predictive, but it's also much more person dependent. So you need to fine tune your models to particular people you're interested in. But 1 million question you raised, like what is normal? Or actually what is stress? Is it good or is it bad? When we talk about acute stress, is it because someone is enthusiastic, excited, or is it because someone is in trouble? Same about relaxation. Like, is it about someone being overworked, or actually everything is going to the better? Or like, what is normal state? Is someone in coma, or is trying to relax, or it's just normal state? And then in many cases, again, like the question is how to get the right metadata, how to get the right interpretation, and how to link it to different contexts. And then this is, again, a very interesting task where change detection, predictive analytics, context awareness come into play such that we can better understand the problem, we can better understand labels, we can better understand reasons, we can explain things better. So there are also other domains where concept drift has been studied recently, but I will skip this part and jump more into conclusions. So if any one of you is interested to learn a bit more about the area of process mining and how concept drift can be considered in that case, I can, well, just talk to me and I will tell more about this part. So few summary slides. So we observed quite a few cases, a few illustrative examples where handling concept drift is important or is essential in predictive analytics. We overviewed a few types of strategies, how concept drift can be handled, or at least like mainstream approaches, what people study. And we looked into a variety of application settings, which on the one hand bring more challenges. So we need to come up with new techniques which actually would correspond to application settings. For instance, how we can think of active learning strategies to cope with concept drift when labels are not immediately available, but we can request them from the user. But also to understand what kind of interesting opportunities we have just relaxing the basic assumptions behind concept drift research and coming closer to real applicational settings where much more data is available and things repeat over time and so on. So therefore, in my opinion, in the near future, we will see some transformation of research in handling concept drift. So current focus is on blind adaptivity, detect change, adapt the models. So in the future, we will try to look into ways how to recognize and use similar situations, how to understand change better, how to add transparency into change detection mechanisms and adaptation mechanisms as well. And I think we will continue also work on this reference framework, which would give an opportunity for different researchers working on concept drift problems to see what actual problems they address and do not address, and then people working on applications where concept drift matter. So we also can show like what kind of approaches are applicable, what are the benefits and then drawbacks of different types of things, and perhaps develop some interesting reference points and standards for this part. And if I would focus on just major challenges or major next steps to be taken, so in my opinion, it's really crucial to go into life, into practice, and then go from experiments on simulated data to real applicational settings, just to see if adaptive applications indeed benefit from concept drift and concept drift detection, and what is the actual situation. And to be able to do that, in many cases, we do need to improve usability and trust such that domain experts can understand what we are trying to achieve with change detection, what we are trying to achieve with model update, how transparent they are, how this can be visualized, explained, connected to business logic, and the like. So I would like to stop here and say a couple of words of acknowledgements and thanks to many colleagues and students who contributed to lots of case studies and development of techniques behind this talk. And especially I would like to acknowledge the work of two colleagues, Indra Žliebaitė and Joao Gama, with whom we are preparing survey papers, analysis of different application studies, and came up with interesting approaches which address application settings. And of course, it's always nice to hear constructive criticism from reviewers. I cannot name them because they're anonymous. And I'm really glad that we had a collaboration with many industry partners to get real data and see what is important for real application settings. Thank you.
Thank you. There's some questions during the talk, but we have time for others.
So you kind of give this characterization of different spaces of your concept drift, but do you have, it'd be nice to see a list of actual problem domains and applications that people are trying to solve where they think concept drift is a problem. Do you have that kind of a listing as well of sort of concrete problems where concept drift happens?
Right. So very concrete problem is in monitoring of industrial processes. So you have sensor data which tells you about the quality of the output. So you need to monitor how good your models are and outputs of those models are. And there are different reasons why they become out of date. And actually, because of the severity of this problem, many people started to look into the domain of soft sensors, like how to build up adaptive sensors which would monitor the stream and adapt to the new settings of the stream. So it's one very big area of where it is recognized to be a very serious problem, and then there is lots of work related to it. So you can think about several real applications related to control systems. So think about the problem of anesthesia control. So you have a patient, and then you need to decide whether you need to inject more or less medicine, such that the person is between the bounds, like not awake and not too much asleep. So typically this is done with controllers. So now people look how to optimize it further by detecting interpersonal and intrapersonal differences and make better adjustments. So if you think about the problem of personalization, this is a problem where people were emphasizing that concept drift matters already, I think, like for 15 years. But if I look what has been done in this area, it's not that much. So
I agree sort of with your earlier characterization that people often talked about the mattering, but actually having the proof in data. So for example, preferences. Do preferences really drift that much, or is it the availability of products that are different, right? And so that you're emphasizing different preferences. Do people actually change all that much, right? It's not clear for a lot of these cases of, you know, a distribution shift is different than an actual concept changing, and both happen. So coming back, I think, to the example where Sue was asking for things changing category, one of the examples of that is email foldering. My view of the world sometimes changes, and I go back to something that I put in one folder, and I put to something else. I've actually changed the concept. And everything else that was automatically categorized now is, you know, up in the air. How would we actually reflect that? How we would show that to the user? That's very different in that kind of case than I think in others. And I think thinking of cases where there's concrete examples of that concept changing is, to me, seems like a challenge.
I mean, you've talked about this as concept drift, but there's a lot that could be going on. It's actually interesting.
what you refer to is actually this separation of real concept drift and virtual concept drift. So, but also what I was trying to emphasize few slides before that is that you can think about different reasons why things change, or why decision boundary changes. So in case of spam classification, okay, well, preferences of people might not change, but because of adversary activities of spammers, you need to detect that your current models are not good anymore, or that I don't know, like maybe you had lots of spam about some rich people trying to give you money away, and then you get more about Viagra spam, and then more about some other type of products, and then just because you have this population shift, your decision boundary changes, and then you need to detect it and then learn it, relearn it. So depending on what kind of change you anticipate, you would monitor either the input. So if it's just about population shift, it is enough to monitor the input space. However, if it is about change in real decision boundary, so you need to get labels. So you need to get proxies of the labels and see if your classification accuracy deteriorates or not, because otherwise you cannot capture it. And then there could be few more distinct points. So this was one of the points I was trying to emphasize, that actually the variety of applications and reasons why things change over time, they can be quite different, and then we need to come up with different strategies to address them. But the original question was like name an application where it is proven that.
Naming an application, I'm just saying it'd be an interesting contribution if we're spending the time not just the ontology of categorizing it, but like, you know, here's a listing of 50, 60 applications and how they map into that space, right?
Oh, right.
Or which models work well in them and which
Yes,
don't.
yes, yes.
I mean,
right?
so that's
that would
the
be
kind
really,
of,
really fun.
right?
This was our original idea, so this is something that we were trying to do. So we've been analyzing lots of papers which were of applied nature, and then they were trying to emphasize what kind of interesting techniques they developed and for what purposes. And so we've been trying to list all kind of application areas, all kind of concrete tasks, and what kind of techniques people were using. But when we looked closer, so then you realize that in most of the cases you don't have strong evidence that particular approach did work well in practice, simply because people played either with simulated data or with some benchmarks and artificially introduced drift, and then we refocused a bit. But indeed, this is an interesting aspect. So this is something that we typically try to do when we perform a case study. So we always try to quantify what is the effect of not capturing concept drift. So you have a predictive model, and what would be an effect so that you didn't detect a change point, or what would be an effect that you detected it too late, or what is the effect that it is detected not accurately. And then you can see what is the actual effect of this misdetection or false alarm on the behavior of the system, or what is the trade-off, like what happens if many more false alarms are triggered, so you relearn the model, what is the corresponding effect on the final performance. But I would say that mainstream research and reality in concept drift area are a bit disconnected. So there were lots of interesting ideas proposed. They were tested on benchmarks, but for some of them we don't know yet whether they really work in practical settings. And then there are a few reasons for that, and then some of them I was trying to list. So there should be a much more systemic view on the problem. So we have predictive analytics tasks, and concept drift is just one of the ingredients. And then you can tell how important it is and how to quantify these effects. So does it answer? Or, I mean, does it relate to your comment?
But are there some examples from industry where concept drift is accounted for and affected, or?
Actually, it is so. Well, you also need to realize that this is quite a large problem space, and in many research areas, the same concept was called slightly differently. So, for instance, temporal dynamics is known to be important, and it has been studied in different areas, including information retrieval, recommender systems, industrial applications. So, for instance, in Netflix competition, well, like you can say lots of interesting things about it, but nevertheless, one of the interesting aspects is capturing this temporal dynamics, like understanding how users' rating scale shifts, understanding how ratings change over time, or how core ratings change over time, and many other effects. And then if you take them into account, yes, you can do better. Again, the question is whether you need to have an explicit change detection mechanism, or it is enough to build evolving models which just relearn or incrementally update. So this is another aspect to it. So if you look into DARPA challenge, to me, this is like very good example of concept drift research, even though they don't name it explicitly this way, but this is a very concrete example of like how you build models which evolve over time.
And financial markets, right?
Yeah.
Right in the whole financial industry that are doing it.
Yeah.
But I don't know, do they predict change, or do they just continuously change the model, just adapt the model reputation?
I have strong negative opinions about
I see the financial modeling world. Okay. On that note, thanks again.
Thank you.